Hello everyone, and welcome to this afternoon's session of PyCon 2019. Just for the last few people who've walked into the room, please try and find an empty seat because we cannot have more people in the room than there are seats. Look for someone with their hand up and there will be an empty seat there. If you cannot find an empty seat, then you may have to find another session just due to fire code regulations. That being said, our next session is about pandas and is by Hannah Stepanek, so please make her feel welcome.
Okay, so I will be talking about pandas, and that does not mean the panda bear. That means the pandas library. And the reason I am up here giving this talk today is because when I started working with pandas, probably 4 years ago-ish now, my mic's out, there we go. Okay, I was a little lost. It kind of requires a shift in thinking that may not be always intuitive for somebody who's worked in Python but hasn't done a lot of data processing. So I'm hoping that you will get out of this talk today a good method for working with pandas, and it will set how to set yourself up for success. So who am I? I'm Hannah. I worked at Intel building a test library for post-silicon validation, and I did that for about 6 years, and 1.5 years of that was spent specifically working with pandas on a data analysis project. So we had a ton of silicon data, and we wanted to do something with it. So that's something being like regressions, or we got really fancy and we're like, we're gonna build models out of it and do some machine learning and stuff. So it ranged in technicality, but my non-relevant experience for this talk is I now work at a nonprofit startup called Hypothesis, and we build a annotation tool, which is a web application for annotating web pages. So what is pandas? This description, quite long-winded, was pulled from the README file. The gist of it is that it's for loading, transforming, and dumping data. But the interesting part I found was actually at the end of this. So it says, additionally, it has the broader goal of becoming the most powerful and flexible open source data analysis manipulation tool available in any language. And I was like, huh, that's kind of interesting, because I've only ever heard of it in Python. So yes, indeed, it is available in other languages. The Ruby version is a bit of a cheat, in my opinion, because it's just kind of a wrapper around Python, but it's there. So this was my question when I was going to give this talk. I was like, that's all great, but why is pandas called pandas? Like, data, pandas, like, I don't see the connection here. But it comes from the term panel data, which is like you can make panels out of your larger panel of data, and that still really didn't answer my question for me personally. I was like, all right, not getting it. But I guess if you say panel data really fast, it starts to kind of sound like pandas. That's my working theory. So what is the underlying data structure? So pandas is built on NumPy, and NumPy often operates in C. And if you know anything about C versus Python, C is generally very fast, and Python is slow. And let's talk about why that is a little bit. So Python has this great garbage collector memory management for you, but that doesn't come for free. That means that it takes more memory to store in data type in Python, and it also takes some CPU cycles. So how the garbage collector kind of like works at a very high, broad sense is you keep track of references to your data. So you end up decrementing and incrementing these counters and references, and eventually when you no longer have any references to your data, we either can just like destroy that object altogether because it's now like references are 0, or if you have some kind of circular loop, like that's where the garbage collector comes in and gets rid of, like knows to destroy that memory. Whereas C, lovely and fast, but you have to do all that like memory management yourself. So anyways, moving on. So this is restaurant data. This is kind of the data set that I'll be working with throughout this talk. So we have the restaurant name, we have the restaurant location, and the location is supposed to be a geocode, but I kind of like BS'd it a little bit because geocodes are really long. Then we have a date of the inspection and a score for the inspection. And if you don't know anything about health inspection data from restaurants, this is publicly available data. So the government or city provides it to you, and it comes in various fun forms to work with. And my boyfriend is actually the author of sketchyfood.com, which I thought was like a really cool use case, like restaurant data, because he actually does use pandas. And so you can see like what are the most dirtiest, disgusting restaurants in your area. So here we're importing this into pandas. We're making a data frame out of it. That's what it looks like. So what does this look like underneath? So it's a bunch of NumPy arrays, essentially. We have an index, which it keeps track of the names of the columns, and then we have blocks, which is a NumPy array of NumPy arrays. And if you're thinking to yourself, like, oh, I've heard those terms in pandas, no, these are not the index and blocks that you may be familiar with through the API of pandas. These are like actually the variables in the code that pandas uses. Not related. So the most important part here that I want you to keep track of is that number up in the right-hand corner. This, as it is right here, takes up 353 bytes. So now we're going to look at a multi-indexed data frame. So what we've done here is we're just taking the restaurant and the location and shoving that into the index and kind of creating a unique restaurant as our index. And how we do this is a two-step process. We create the index, and then we attach it to the data. So that's what we're going to do. So here, what this looks like underneath is we have levels, which are the names of the indexes, and then we have the values, the names variable, which keeps track of the values within each of those indexes, and then those correspond to the labels. So like, for example, diner is at index 0, so we put a 0 where it should go in the data section of the index. And this, hopefully for some of you, you're going, aha, this is compression of data, because we're not repeating the string, which takes up a lot more memory. We're simply repeating an integer. And also, this is why it's very important to normalize your data. For example, if we have a capital case diner and we have a lowercase diner and we also have this mixed case diner, you're not going to get as much compression. And so your data frame is going to be a lot bigger than it needs to be. All right, so we have our index. So now we can attach this to our data. This should look familiar. We still have the index. We still have the blocks. We just have less columns now. But this, unlike the flat data frame, only takes up 261 bytes. So we've a thirded our memory here just by storing our data in a different format. And this is the first reason why you should use a multi-indexed data frame. So that's great, but we don't often when you load data in pandas, you generally have to load it as a flat data frame and then convert it. So this is kind of just how you might do that. You basically just called set index, and you pass in the columns that you want to be indexes. And the important part here on this slide is the in place equals true. And that is very important in pandas, because if you don't do that, you will be duplicating your memory, which kind of defeats the purpose of using a multi-indexed data frame in the first place. It occurs as in place equals true or copy equals true. The copy equals false. The copy equals false is a little finicky. I think the documentation says something like it avoids copying when possible, which is like a little vague. So you have to be a little careful there. But anyways, so loading and normalizing data. So I'm going to be talking about the read CSV function briefly today, because I don't have a lot of time. But my recommendation when loading data into pandas is always read the loader's documentation for the loader that you're using, because there are a lot of options in there for kind of like normalizing your data while you're loading it, which is fantastic because means you don't have to load as much data and then sort and filter it later. All right, so loading data. So if we just load the raw inspection data from New York City, this is kind of what it looks like in its raw form. New York City luckily gives us a CSV file, which is a lot nicer than some other cities. But anyways, so here we have these not applicable values. And we also have, you notice, like an empty string for the inspection date. So raw data is kind of ugly, and it's important to filter through it. So in this scenario, what we can do is just mark those with like a none type, essentially. Be like, we don't have this information, and we can decide what to do with that later, like whether we drop this data or keep it and do something else with it. I don't know. But the point being, we want to convert those to nans. And nan stands for not a number. It comes to us from NumPy. My high-level interpretation of it is that it's a none type for pandas. And so here, we're just converting them to nans. So we have this NA values, and then we pass in like which values we consider to be nans when we load the data. It's always really important to understand the library that you're working with and its limitations. So in this scenario, the question is, okay, so what if we have a restaurant named Nan? What do you think happens? It's like, crap, this is not good. So it converted it to a Nan, which we don't want to do. So here, we can just say keep default NA equals false, which my interpretation is like pandas don't think you're smarter than you are, and don't do that. So lastly here, you'll notice that if you just load this raw data, and you look at the score column, which is generally an integer from 0 to 100, at least we hope it is, the data type on it is an object. And an object in pandas is basically a string. And so strings are larger than integers, right? We would prefer if pandas made it an integer, it would probably save us some memory. But pandas didn't do that. And why does it think it's a string? Pandas tries to infer the data type, but since we had those not applicable values in that column, even though we converted them to nans, it still kind of interpreted the data type beforehand as a string type. So what we can do in order to kind of like save memory and get things in the right types to begin with is when we load the data is to pass in the D type for each of the columns. So that's what we're doing here. You notice we convert the date string into a date time. We're using an int date, which is like the smallest integer we can use, and the other one's string. Okay, so here is kind of a table of, sorry, it's a little fuzzy. Here's a table of the different data types. So we have the pandas data types, the Python types, and then the NumPy types. So you're like, this is great, but why is this important? So I mentioned earlier that we go from Python to NumPy to C. And ideally, we'd like to run in C as much as possible, but we can only do that if our code is translatable into C, which means that date time is not really translatable into C. So what we should probably do if we have any date times is convert them to like a milliseconds at the epoch or something, like an integer value, which is easily translatable into C. Thus, our code will be more performant. So what does this look like in terms of the actual memory savings that we get? So if we look at that score, it was originally an object, which took up 232 bytes. We made it an integer, and now we're taking up 108 bytes. So that's like, we halved our memory, which is great. And this is only 4 rows, keeping in mind we're probably not dealing with 4 rows. Since we're working pandas, we're doing big data processing, we probably have thousands of rows. So this is a huge memory savings. All right, analyzing and manipulating data. There are 2 kind of documentation links here. The first one is basic indexing. Like, you're a beginner, you know nothing about pandas. How do you get your data out of it? The second one is one that I refer to a lot, merging, joining, concatenating, because I can't remember the difference, so I always have it open. So indexing. Pandas has this really nice, what I like to call dictionary syntax, which you should be familiar with if you're familiar with Python. So you can basically treat the column name as a key, and if we want to get like all the scores, we can say df of score, get all the scores back for the restaurants. We can also do something a lot fancier than that with Boolean expressions, so we can grab all of the restaurants with scores greater than or equal to 90 earlier or after April 18th. Cool. Okay. So there's also iloc and loc that you can use for grabbing data out of your data frame. A lot of people can't remember the difference. The way I remember it is I stands for integer, and that's kind of what we use to get the data out with iloc. So you can grab like row 0 out of the data. You can also grab the even rows out of the data. You can also use like a list syntax, so you can use like a colon, comma, or sorry, like colon to 10, and it'll give you back like 0 to 10 rows of your data set. I don't really find myself using this a lot in practice, because I'm not usually after a particular row in the data. But here, maybe the inspection date is wrong, and you want to modify it to be correct. You can do that. All right, loc. Oops, it's cutting out again. So loc, it has two things here. You can specify the index and then comma the columns. So in the first scenario, and if you don't want to specify one of them, you can either use like colon, comma, if you don't want to specify the index, or you can just leave off the columns altogether, which is what we're doing in the first scenario. So here we're just grabbing all of the data for diner. The second example, we are grabbing a particular diner restaurant, assuming there are multiple locations for a diner, and all of the scores for it. Again, we can also do something super complicated and fancy with Boolean expressions. So here, we're grabbing all of the restaurants with scores greater than or equal to 90, and I've thrown something in here a little bit extra. So index, get level values, restaurant. So basically, we only care about the names of the restaurants. We don't want the whole entire like sub-data frame. OK, merging. So the merge for pandas pretty much works like the merge for, if you're familiar with database merges, same thing. It has inner, outer, left, and right. And I'm going to go over inner and outer today. So say we have old data and new data, and we want to get the data in common between those two sets. We can use an inner merge to do that. Alternatively, if we have the old data and we want to update it with the new data, and the new data may also contain the old data, we don't want to repeat that data in common. So we can use an outer merge for that. Oh, and one thing before I move on. So you'll notice that these data frames are not multi-indexed. Merge doesn't work with multi-indexed data frames. You have to have a flat data frame to use merge. So join does work with multi-indexed data frames. So here and this is actually the case generally, the cities don't provide the geolocations of the restaurants. You have to look at that information separately. So here we have the restaurant health inspection data, and then we have another table that contains the locations of all those restaurants, and we're just joining them together. And you'll notice that we don't have to specify the index to join on. The tables are already indexed, and join automatically determines that for us. The next line there is just when we do this join, the location ends up being a column in the data as opposed to an index, so we're just telling it after the fact to set it as an index. Concatenate. So we can also concatenate and repeat data if we need to. So here we have inspection data from 2 different cities, and while the line is the same, chances are that's actually a different restaurant. So, because it's in a different city. So here we're actually concatenating the data together because we do want the data to be repeated. Apply. So apply is probably one of the most overused and incorrectly used functions in pandas, I think. You really shouldn't be using apply ever unless you have to write a custom function. And you have to apply it to every single row or every single column in your data set. And this is an example of such a case. So we're trying to just convert the score into a letter grade for each of the restaurants. And so here we can use apply to do that. So we literally want to take every single value in the score column and convert it to a letter. And so here we make a grade function, and then we pass in that function into the apply, and then we say axis equals 1. So you can say axis equals 0 or axis equals 1. Axis equals 1 in this case because we want to apply it to every single value in the row. Yes, every single value in the column, meaning we want to go per row. So here, this is a great example of when not to use apply. And unfortunately, this isn't exactly in the documentation anymore. I think they have like mp.sum, but this is pretty much from the documentation. But you don't want to do this. So let's talk about why that is. So here we can do a df apply and pass in the mp.mean function and specify the axis, and we can calculate the mean score for each of the restaurants, and that's fine. It works. It's probably pretty slow, but it works. Alternatively, you may notice that there are functions that exist off the data frame as well. They're kind of built into pandas. So we also have like a dataframe.mean that we can call. And again, it works, like they do the same thing, ultimately. But one of them is much slower. So the first case is 2 times as slow. And let's talk about why that is. So the df.apply several layers down ends up ultimately calling into what df.mean calls into almost instantly, which is ultimately like a numpy mean. But the difference is that df.apply loops in Python and calls into mp.mean on every single value, whereas df.mean calls into numpy with all the values and loops in C, and then returns the result. So it's like looping in Python versus looping in C. Which one is faster? I'm just shocked. So here, again, this isn't 2x slower forever. This is like n number of rows slower, which is pretty substantial. So don't do that. If you have a function off the data frame, use it. Group by. So chances are, if you're working with a large data set, at some point you're going to have to run a group by, which is basically put our data into groups and run some kind of aggregation function over it. So in this example, we're grouping our restaurants uniquely, and then we're counting up the number of scores that or a number of inspections that have been done on each restaurant. And ta-da, it works. So we have our group by, we pass in the indexes, which happen to be the same indexes as we've indexed our MultiIndex DataFrame by. And then you have an aggregation function at the end, so in this case, count. And then I'm just doing something really subtle at the end here. Because we're counting the scores, it's going to output the name score for the data instead of what we'd like ideally now to describe our data as the total. It's no longer a score, so I'm just renaming it. Here, this is something that I see often people do a lot, which is a mistake. The group by will also return an iterable, which in turn will let you iterate over the groups and call a function on them. You can do that. It's really slow, but you can do it. The difference between like this slide and the last slide, though, is the last slide actually returned a series to us, or like a smaller data frame. It didn't put the data back into the original data set, whereas here, we are putting the data back into the original data set, so there is a subtle difference there. But in terms of time, and of course, we didn't have to put the data back into the original data set. We could have made like a mini one as well. But this is 2 times as slow. And it's, again, because we're looping over those groups in Python as opposed to calculating the groups and calculating the data and then sending that to the count function in C land. So again, this isn't like 2x slower forever. Depending on how many groups you have, this will increase accordingly. Pivot tables. So pivot table is kind of another one of those, what I would call overused functions in pandas. My recommendation is you really shouldn't be using it unless you're doing it as an initial first step. So it's really great if you have a huge set of flat data and you want to just like completely reformat it and aggregate it and do a bunch of crazy stuff initially. I think it's great for that. it gets the job done a lot faster than doing all those steps incrementally. But if you are using it as a substitute for a group by in your code, don't do that. And I will show you why. So here we're just essentially performing that same group by operation that we looked at earlier, where we're counting up the number of inspections per restaurant. And here, again, we can do this with the group by as well. This is the same group by scenario. But one of these is really slow. So pivot table is 2 times as slow. And I'm cheating a little bit here because pivot table is a flat data frame, and the group by case is a multi-indexed data frame. But that's the advantage of using a multi-indexed data frame, is that you can do group bys a lot more quickly. So this 2x comes because the multi-indexed data frame is already indexed, like we've already calculated those kind of like unique pairs and stuff. Whereas in this scenario, with a flat data frame, we haven't done that. And so pivot table has to do that on top of it. So, and this leads me to my next topic, which is choosing the right data frame. So depending on what you're going to be doing with the data, you may choose a different format to represent your data in and pass it around your code. So if we look at the flat data frame scenario, this is what it would take to get our data to calculate the number of inspections per restaurant and get it back into the original data set. It's a lot of code. We got to do a group by, and then you'll notice we have this as index equals false in there. That basically just means that when group by returns the data frame, it doesn't return it as a multi-indexed data frame. It returns it as a flat data frame, which just makes it easier for us to merge it back into the original data set. But again, we're renaming the columns, and then we're merging them back together. Get our results. However, if we chose this format instead, which is a multi-indexed, multi-level-column data frame, sounds very fancy. So here, again, we have the unique restaurants in the index, and we have multi-level columns as well as multi-level indexes. So here, we've split out each inspection into its own column by inspection date, and then the score is represented as the data point in each of those. And you'll notice that we have some nans in there because not every restaurant was inspected at the same time, but these are integers. They don't really take a lot. They don't really take up a lot of space. It's not really too big of a deal. In order to get that same result of counting the number of inspections per restaurant, this is really simple now. We don't have to run a group by at all. We can just run a df.count. And you'll notice that that function is right off the data frame, right? So it means we're, again, like looping in C, and we only have really like 2 rows to loop over here anyway. So it's really fast. And how much faster is it? So here, there's a difference of 4x in this particular example. Obviously, the more groups you have, the more rows you have, the more that's going to grow, which is why it's very important to choose the appropriate formats for your data frame initially. Don't be afraid to spend some time thinking about that and the ways you're going to need to transform your data and how your data frame will affect that. So lastly, we looked at that apply case earlier, and there are some scenarios like that example that I showed where you just have to use apply. You have this custom function, you have to iterate over every row in your data set, you have to apply it, it's just the way it is. So how can we improve the performance of that? Because that ends up being really slow for large sets of data. So this code is actually the code in Pandas, the implementation for apply, deep down. So we have this loop, it iterates over series generator, so that's either iterating over columns or rows, and it grabs our value out of that iterator, and then we have this self.f, which is the function that you passed into apply, and it passes in the value, and it gets the results, and then does some other appending, whatever. But the point is, it's a very simple implementation. It's not really that hard to implement yourself. So that's what we're going to do. We know that C is fast. We know that Pandas has some built-in functions that essentially implement apply for us. And so we're just going to implement our own custom apply that's super fast. So here and we're going to use Cython to do that. So we're going to write Python code. And then we're going to have Cython compile it into C. And then we're going to call our C function from Python. So here, we've implemented our C function. So we're looping for I in range, and we're keeping it really simple because the more like Python data types that we try to pass into C land, the more complicated and convoluted and potentially not C it's going to be. So we're just passing in essentially like an array of values, and we're looping over that array of values. And for each one of those values, we're changing it to be a letter instead of a number. OK, so here, how we do this from the Python land of things is we take our score column, we convert it to a list, we call our grade function and note that we're doing this in place, so we're not actually getting anything back, we're just modifying the scores in place. And then we create a series out of it, we connect the index that we were using before to it, and then we update our data frame with our new data. So how much faster is this? This is an exciting moment. So this is like literally how much faster it is. With 40,000 rows, it takes about 4 minutes to run the pandas apply, and it takes like 5 milliseconds to run the custom apply. So highly recommend doing this if you run into a case where you have to use apply in your code. So in summary, avoid looping, normalize your data, use multi-indexed data frames, use in-place operations, and take advantage of Cython when you need to. And that is it.
Thank you very much, Hannah. If anyone has questions, there are microphones located in the aisles here. Please queue up. Please be asking questions, not raising comments or telling stories, please. Question over here.
Instead of using .apply, would you be able to use .map? And how much faster would .map be if it's only iterating through a particular column?
That's a good question. I'm not sure. I'd have to look at .map and the implementation. Yeah. I don't know.
Hi. So for that particular example, I mean, for one, .apply when you use access is equal to 1 is essentially an iter rows. In that particular example, you could have just used the numpy.where and just like created a series of masks and like replaced the values where it was true and where it was false without having to go into Cython.
So you're saying like looping over the columns instead?
No, you don't. So you don't need a loop at all, honestly, in Python. Like all you needed to do in that situation, if you had that example, you said less than 70 and greater than 80 or something like that. So if you use a numpy.where, you can replace, or I mean, even Pandas has it. It's a little slightly slower, but if you do a numpy.where, and first condition, with the condition, it returns you like an array of booleans.
Yeah.
Why didn't, I suppose, like, why would you ever use .apply?
So, I mean, there are definitely, like, if you have a custom function, can you, in your scenario, can you pass in, like, a custom function? Like, even though I know you're, like, mapping the booleans, but are you applying, like, a custom Python function?
I'm just trying to think of like any way where you're actually looking at like the any situation where you really have to look at the row.
Yeah.
Like each an individual row.
I mean, I think in that scenario, like it's a conversion of like a value that's in every row of your data. So I mean, I think in that scenario, yeah, like you just have to do that. But I mean, yeah, it really depends on your data set. Like maybe you don't have to do that for your data set.
We're still taking questions. If people could take any conversations they want to have out into the hallway, that would be most appreciated. Thank you very much. Next question here.
So I might be doing something wrong, and this is hopefully a good question. I'm currently using apply to create effectively a compound key between two other columns in a data frame, because I also need to be able to take that value and pass it around. And the function that I'm using is a SHA-256 function, so that I can obfuscate the data because of the nature of it. Is that okay, or should I be doing something different?
I'm sorry, I was having trouble hearing what you were saying.
Okay.
I apologize.
Should I start at the beginning?
Sorry,
Yes.
could I repeat, please? Anyone who's having a conversation in here, could they please move out into the hallway now, please?
I can also just, like, if you want to come up here, I can
Sure.
answer questions, like, in person.
Afterwards?
That might be easier.
Okay.
Yeah. Yeah, just because there's a lot of echoing. I'm sorry.
Are there any more questions? Thank you again, Hannah.